today we're going to mostly look at the second type. The first type is easy to predict because you basically know where the disturbance geometric non-smoothness is. And usually that's a way for you to control transition, right? So you don't really need to predict it. So we'll start from the second way of transition, natural transition. And the key to analyze how transition happens is perturbation analysis. So we have the perturbation analysis starts from Navier Stokes equation. It starts from the unsteady Navier Stokes equation. So du dt plus u dot with grad u is equal to minus 1 over rho times grad p plus, let's just write Re inverse times the Laplacian of u, right? So this is the viscosity 1 over the Reynolds number. So if you non-dimensionalize things, this will become 1. So let's just start from the non-dimensionalized Navier Stokes equation. All right. So we are looking at a small disturbance on top of a steady state laminar boundary layer. And the assumption is that we can decompose this u into a big U, which is a function of space but not time, plus a u prime that is a function of space and time, such that u prime is much, much less than the big U. So this is the fundamental assumption in the small disturbance analysis. The small disturbance is small, but is a function of time. The base flow, big U, is not small, but it is not a function of time. Okay. All right, so once you make that assumption, by plugging the decomposition into the equation, we're going to find out, first of all, the big U is going to satisfy the steady state Navier Stokes equation. So the big P is the pressure, is the steady state pressure corresponding to the steady state velocity. So that is just the base flow satisfies the steady state Navier Stokes, which we already analyzed a lot in our laminar, in our thin layer approximation, right? So this is the U that we use the thin layer approximation and everything because it satisfies the steady state equation. And what is new is the governing equation for this small u prime. So the small u prime is governed by the linearized Navier Stokes equation. So first of all, the time derivative only applies to the small u prime because the big U is steady state. And the advection term is going to be split into 4 parts, right? Because it's a quadratic term. And if you split the u in a quadratic term into 2 parts, you get 4 terms. The first term is simply this, right? And we're going to cancel all of this using the steady state equation. And the fourth term, the interaction between u prime and u prime itself, can be ignored because u prime is very small. What is left is the middle 2 terms. One term is big U dot with grad u prime. The second term is u prime dot with grad of big U. Okay. All the other terms are linear. So the grad p has split into 2 terms. One term is just this, gets cancelled by the big equation, and the rest is grad p prime. And also the same thing. We have the leftover term Re inverse times Laplacian of u prime. So this is called the linearized Navier Stokes that governs the evolution, the unsteady evolution of a small disturbance, which ultimately governs the evolution of the unstable waves evolving in the boundary layer.
Should that be minus?
Minus, yeah, thank you. Yeah.
density were
Density is non-dimensionalized to 1 here.
to 1.
Yeah. Okay. All right. So to write these equations in a thin layer, taking advantage that this big U is mostly horizontal, right? So big U in the x direction is much larger than the U in other directions. We can write this as so these are all vectors. These are all vectors. And let's write the vector U prime as U prime, V prime, W prime. Okay, these are scalars. So these are vectors. Okay, so now let's go into scalars. And big U vector is equal to big U and all the V's. The V's, there is no W, so V is much less than U. Okay, so with this assumption, the equation becomes 3 equations. So the first equation is a streamwise velocity. It's going to be added with the only significant terms. The only significant term in this is the streamwise big U, right, times the x derivative of U prime, of small U prime. Okay, we know that the big U varies slowly in the x direction, but the small U may not. The perturbation may vary not slowly in the x direction. It may have a wave-like structure in the x direction, so we cannot ignore this term. Okay, and the only significant term in this one is the V prime. So that's this is also vector. V prime is this direction. And that is because partial big U, partial Y is not negligible, right? This is a very large term. So this is equal to minus partial P prime, partial X, plus RE inverse times Laplacian of U prime. And the other 2 equations are a lot simpler. Again, this is only advected in the x direction, but this is gone, right? Because there is no significant variation even in y for the y direction velocity. This is equal to this plus the same kind of terms on the right hand side, and the same equation for W. So we can actually ignore the equation in the spanwise direction, in the W direction, because there is this theorem called the Square's theorem that says if we are interested in the fastest growing instabilities, then it has to be only 2-dimensional waves. Okay, this is saying that like if you have if you have an instability mode that involves a non-zero spanwise velocity, then you can always find a corresponding 2-dimensional mode, which means a mode that does not have any velocity in the spanwise direction that grows even faster. Alright, that is also saying that the first mode that is going to become unstable, and also the fastest growing unstable mode, has to have 0 W velocity. So fast growing modes have W prime equal to 0. Okay, so with that, we only consider these 2 modes.